Hello and welcome to Guessing the Specialist exam. This is part 4. Last year I did it, but this year my past students are doing it. They've got this tutoring company. If you've got like a younger brother or sister who's just getting started with methods and specialist, sign them up, bring them over here. It'll be awesome. Alright, on to the first question. Alright, it's Tech Active this time. Have a try at it and then I'm going to jump into it. Alright, so it's everyone's favourite question, an inclined plane question. I'm going to draw this. Alright, there's my drawing of it. I have a mass of 12 kilograms. There's a string pulling it up, or trying to pull it up the inclined plane, 29 newtons. I've drawn in my normal contact force. Don't know if we'll need that, but the angle's 25 degrees. Okay, so what do we need? Well, let's find out how much force is going straight down, first of all. Force is equal to mass times acceleration. The mass of this object is 12, and it's being accelerated by gravity at 9.8. Alright, 12 times 9.8. So, there is 117.6 newtons of force being exerted straight down. But the question is, how much force is being exerted in that direction by our box? Now for that, it's a really good idea to tilt your head and use this as your I and your J components. So if I take this line and transfer it to there, right, what I actually have is a vector moving in the third quadrant of my I and J axis with a magnitude of 117.6 and an angle, hopefully you can see this, angle of 180 plus this bit here, which is 65. So with an angle of 245. Alright, so that means that if I want to know how much of this vector is in the I direction, I can just do the magnitude of it, 117.6, cos the angle, 245 degrees. Alright, when I do that, I get negative 49.67. That makes sense, because it's moving in this direction. This is our I direction here, so we would expect a negative value. So that negative 49.67 is this value right here. Okay, now what's the net force in this direction? Well, the net force in this direction is the force of the string plus the force that the object itself is exerting due to gravity. So the net force of this object is negative 20.67 newtons. There is a net force of negative 20.67 newtons acting down the plane. But we don't want to know the force, we want to know the acceleration. Luckily, we know that force equals mass times acceleration. And so the force, if it's negative 20.67, is equal to the mass 12 times the acceleration. And we can easily find A now just dividing both sides by 12. Now, acceleration is equal to negative 1.72. Now, why is my answer negative and all of our options are positive? Because the question says acceleration of the box down the plane. Accelerating down, that's a negative acceleration. So our answer here is A, and we can move on to the next question. You thought I forgot. Next question. I love these questions here. Tech Active, but I don't think your calculator is going to help you very much. Have a try. Alright, 2 almost certainties in this world. 1, a question like this will be on the exam. 2, half of the students won't know how to do it. So don't be in that half. Okay, what's going on? What do we need to do here? We kind of need to go a bit trial and error-ish, but clever. Okay, we've got 4 options here. And I really am enjoying this question, right? Because normally what I would do in questions like this is look in quadrant 1 and look at what the gradients are doing in quadrant 1. But the problem here is that in quadrant 1, the gradients are positive for a little bit, like this one's positive, and then it's 0, and then it's negative. Now, I haven't seen questions like this before, but that's quite cool. What am I noticing that's very interesting? I'm noticing that when x equals pi on 2, the gradient is always 0. It doesn't matter whether y is 1, 2, 3, 4, 5. Doesn't matter. When x is pi on 2, the gradient is 0. So basically what we can do here is put x equals pi on 2 into our 4 options here, and just a random y value, I don't know, like y equals 2, and just like see what happens. Okay, when I put 2 for y and pi on 2 for x into this equation, 2 cos pi on 2, that's equal to 0. That's good, because my gradient there is 0. And so you might be tempted here to stop and go, yep, I've done it, my answer's A, I'm finished. You really need to be more thorough than that. You really need to check the others just to check. Okay, so what happens here? If I put 2 in for y and sine pi on 2, sine pi on 2 is equal to 1. So 2 times 1 is 2. All right, so by a process of elimination, this is definitely not an answer. Okay, so checking part C here. Pi on 2, okay, times sine 2. Sine 2. Okay, what's sine 2? Well, 2 radians is like over here somewhere. Whatever it is, it's not 0. So pi on 2 times whatever that is, which is not 0, is not 0. So I'll just write not 0 there. Now, this is tech active, so you can just type that into your calculator. And what will your calculator say? Not 0. Similarly, for part D, if I type that into my calculator, I don't know what I'm going to get, but I'm not going to get 0, which is what I want for all those values. So it turns out we struck gold straight away. The answer is A, but you really do want to check all 4 because these questions are super tricky, and quite often if you test one point, you'll find 2 solutions that work for it. All right, celebrating. Next question. All right, it's tech active. Have a play with it. See if you can come up with an answer. Now, I was going to skip this question. I wasn't going to do it. I was going to do something different. But I gave this question to one of my students, one of the cleverest students I've ever taught. Hey, mate. And he got it wrong. Maybe you don't know that yet, buddy. So let's take a look at it and see what happened. All right, so it's worth understanding what this question is. We have a plane. We have 2 vectors that are sitting on the plane. Right? 3, 3, 8 and 1, negative 3, 2. Vectors on the plane. We need to find a vector that's normal to it. That's popping straight out of the screen there. So right angles to both of those, cross product. Now I've got my calculator, so my calculator can do my cross product for me. All right, so let's see if I can make this work. Options, mat, choose this one here, cross product. So now that I've got that, I need to enter those 2. All right, so to do that, I'm just going to exit, and then click math, and then click this matrix vector thingy, and arrow across. This is the golden one here, the 1 by 3. So it needs to look like this: 3, 3, 8, and then a comma, and then another one of those. Oh wait, did I just type 3, 3, 3? 3, 3, 8, and then another one of those, and the other one is 1, negative 3, 2. And close that up. All right, and that is my answer. 32, negative 12. So what have I just found? I found this vector that's normal to the plane, and it's 32, negative 12. So there's my answer, 32, negative 12, 30i2j, negative 12k. And so what my student did, who was actually proofreading these questions for me, said, this question's wrong, right? Instead, part A should be 30i plus 2j minus 12k. Pretty decent assumption given he was proofreading my work. But, right, read the question. Determine a vector normal to the plane. And we've done this trick before in just a previous video. There are an infinite number of vectors that are normal to this plane. So, any vector that is a multiple of this vector would do the job. So, of these 4 options, something that fits the bill would be to multiply the entire thing by negative 2. If I multiply the entire thing by negative 2, I now get negative 60, negative 4, and positive 24. And that works for us, and the answer is B. All right, on to the short responses. All right, it's Tech Active again. Have a try at it. See how we go. All right, I like this. We've got two astronauts floating through space being followed by here. Part A says, prove that the astronauts will never collide. Okay, what needs to be happening for the astronauts to collide? Their I components, their J components, and their K components need to be equal at an instant in time. Okay, so let's look at what their I, J, and K components are step by step. Now, when you're doing these kinds of things, often the equation is given as like 3j plus t something. You really want to convert it to all i's, all j's, all k's, right? So here, the I component, there's no starting I component, but there is like an I component that is has a variable t with it. So 2ti. That gives the position, the I component of our astronaut at any given time. In terms of its J component, we've got the 3J and we've got the 2TJ. So 3 plus 2TJ. There's our J component, and our K component is just negative 2TK. J. Okay, that's done. We can do exactly the same thing for astronaut B. Okay, far more useful now. Now that we've got that, look at their I components, look at their J components, and look at their K components, and find out what times their I components are equal, their J components are equal, their K components are equal. So, here, we can say that 2t equals 5 plus 3t, and we can find at what time those I components are equal. 3t minus 2t is t, negative 5. At time, negative 5. A lot of people work with the assumption that you can't have a negative time, but like, I remember stuff that happened yesterday. So, yeah, sure. It doesn't say like t greater than 0, so why not a negative time? Okay, why don't we look at our J components now? So 3 plus 2t equals 8 plus 7t. 7t minus 2t is 5t. 3 minus 8 is minus 5. T is negative 1. So that's it. We've really proven it. And let's look at why we've proven it. There is only one time when their I components, their position, their x position in space is the same. And that's time negative 5. There is only one time when their y position in space is the same, and that's negative 1. For them to collide, they have to have the same x and y position at the same time, at least. They would also need to have the same k position in the z-axis. So these two are definitely never meeting because their I and J components do not equal each other at the same time. So that's part A. We've proven that these astronauts will never collide. Now this is kind of bonus content because you're not going to have this in an exam, but I thought it's worth exploring here. These are our two astronauts, A and B. The coordinates of our astronauts, if you can see just over here, they're given by 5 plus 3t, 8 plus 7t, 2 minus t, or for the blue one and for the red one. If we move time, if we move our astronauts through time, you can see they're not going to run into each other. They sort of fly past each other and then off into space forever and ever and ever. We can sort of show that just maybe a little more clearly by turning a trace onto their paths. Okay, you can see they never whack into each other, right? Blue sort of seems like it's ahead of A kind of thing. Alright, so there's our basic idea. That's part A. Our astronauts never collide because they don't share the same spot at the same time. Now the good news is that part A was the easy question. Part B is the difficult question. It's the harder part. It says, determine the minimum distance between the two astronauts. Now again, you're not going to have this in an exam, but it's worth showing you what that looks like. So here are my astronauts again. Let's draw a vector between our two astronauts. Alright, so there is the vector between our two astronauts, this black thing here. It's 3, negative 5, 0 at the moment. Now, as I move through time, that vector gets big, it gets smaller, and then it gets bigger again, right? In fact, maybe I'll just ask the technology to give me an idea of how long that vector is over time. This value here, this 4.33, is the magnitude of that vector right there. So we can see way over here at like a really negative time -5, the magnitude of the vector is 20.22, very long. As we move forward in time, it gets smaller and smaller and smaller and smaller, smaller. It's 4.03 about there, 4.01 about there, 4.16 there. So there's some point where it's about 4 meters, okay? So that's what we're aiming for when we start doing this without the help of our little GeoGebra thing, which we're not going to have in an exam. So hopefully now it's pretty clear what we should do. This is astronaut A. This is astronaut B. If we want the vector that connects astronaut A to B, in other words, we're trying to find vector AB, we do that how we would connect any other set of points, right? We do vector B minus vector A. So we do 5 plus 3t, this is vector B, minus vector A. And that, I'm going to write it in column form. That is going to be my I component of the vector AB. A plus 7t minus 3 plus 2t. Be careful there. And then finally we've got 2 minus t minus 2t. So plus 2t. Alright, we've got something there. I can tidy that up a little bit, group some like terms, etc. So now we've got something like this. This gives us the vector connecting astronaut A to astronaut B at time t. Now we don't care about the direction of it, we care about the magnitude of it. So how do we find the distance between our two astronauts? The distance between our two astronauts is going to be the square root of 5 plus t squared plus 5 plus 5t squared plus 2 plus 2t squared. This is the magnitude of the vector that connects our two astronauts. This is the distance between the two astronauts at any given time. It is at this point that we should be very, very thankful that this is a tech active exam, because we're essentially finished. If we sub this into our calculator with y equals x, we can just graph it and see what the distance is at any given time. I hope you're all screaming at the screen then and noticing my mistake here. That's like a big oops. We've got 2 plus t squared. 2 plus t squared. Okay, we can graph that. So here's one I prepared earlier. Let's double check it. 5 plus x squared, 5 plus 5x squared, plus 2 plus x squared. That looks good. Let's draw it. And we get this thing. And that's what we expect when we saw our astronauts. Because this is time, and this is the astronauts and how close or how far they are. Let's do an auto zoom, see if that makes our life a bit better. Oh yeah, I like that. Alright, we can see our minimum right there. Let's G-solve it, find our minimum value. It's right there. Now, what are we asked? Determine the minimum distance between the two astronauts. The minimum distance is our y value. So our minimum distance, min distance, is 4.009 meters, I guess. I don't know if we're told it's meters. Let's assume it's meters. Minimum distance, 4.009 meters. You might have been asked what time it is. It would have been 1.1 seconds in the past. There is our answer. I like these. I love this. I love that we're using our calculator to do some like funky stuff. Good question. All right, celebrating. And last one. All right, last question. A child throws their toy, blah, 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 blah. Now, if you've watched the previous videos, you'll know we had a child throwing a toy. That was a projectile motion question. But this question is framed in a different way. We're given an acceleration function in terms of velocity. So this is something that you want to keep in mind. check your acceleration functions and check what they're in terms of. If they're in terms of anything but time, then you've really got to look at your formula sheet and things like this. Now, if you've got an acceleration function in terms of velocity, you really want to be thinking about this formula here, v dv dx. So this is the equation that we're given, and I'm going to say, okay, acceleration in terms of velocity, we can replace our acceleration with v dv dx. While I'm in the mood for replacing things, I notice this g here. My formula sheet says gravity is 9.8 meters per second. Okay, grand, I love it. That's where we're going to start from. So I'm going to get this dv dx by itself by dividing both sides by v. And then just because I can, I'm going to get rid of this negative 0.05 by multiplying everything by 20. Now there are different ways that you can proceed from here, but eventually we want to end up with an equation that is x equals something. Right, so the way that I'm going to go about that is by flipping both sides of my equation to get x onto the top. That makes a lot more sense, right? My equation's in terms of v. If you think about all the equations you do in math methods, you've got dy dx equals something something x, right? So when you've got an equation in terms of v, it's nice to have dx dv on the bottom. Now we can integrate that. Now, I got called out in the comments of a previous video because I used partial fractions when I could have used the fact that if you've got f dash of x over f of x, you can integrate really simply that way. So here is my chance to redeem myself. I almost have f dash of x over f of x. If I just brought 10 out as a factor, negative 10 out as a factor, I get negative 2v over negative 196 negative v squared. Now this, negative 2v, is the derivative of negative 196 negative v squared, so I get to use my funky little rule. Before I do that though, I might just notice that I've got a negative over here, I've got a negative over here. I can actually rewrite that as just 2v positive 196 positive v squared. That's an equivalent state. So when I integrate that, when I've got f dash of x over f of x, we're going to get x equals, there's my negative 10, and then ln, whatever was on the bottom. Absolute values. Don't forget your plus c. Alright, and speaking of plus c, that's probably what we need to do next, right? So what do we have? We need some sort of initial condition, or some sort of condition. Alright, so the child is throwing from a height of 1.2 meters. Alright, so when x equals 1.2, velocity, initial velocity, 5. Alright, so let's sub 1.2 and 5 into our equation, see what we get for c. I am being super lazy here, but something I want to mention, solve n 1.2 equals negative 10 ln. We've got our absolute values here. You can find that if you go into options, more numeric absolute value, put our absolute value in there. Is it silly of me to type all of this in to solve n, or should I just rearrange it? Because it's like one step of rearranging and just type it into a calculator without using solve n. Your thoughts? Okay, what do I get? I get an answer, press exit. 55.18. Okay. There we have it. We have an equation, and think about what this equation is. This is an equation that tells us the displacement when the velocity of this object does certain things. There's sort of two ways you can go about this. We want to know when this is at the top, when this gets as high as it can possibly go, how high is it? Okay. So how do I do that here? Well, when an object that you've thrown into the air gets as high as it possibly goes, that means for an instant, it stops moving. It's not moving up, it's not moving down. In other words, its velocity is 0. So when I sub v equals 0 into this equation, right there, I get x equals 2.4004. Right? That means that when it's at the top, when it stops moving just for that instant second, it's 2.4 meters high. Now the ceiling, we can read, is 3 meters tall. This is only going to get to 2.4 meters tall. 2.4 is less than 3. I feel like this is an important statement. Therefore, not hit ceiling. Now, I kind of mentioned that there was sort of two ways that you could go about this, sort of a different way. One way that you could go about this is to graph this equation. So this is my equation. I've typed it in. Now, you need to be careful when you type this thing in. Let me find a spot. You need to be careful when you type this in, because I've typed it in as y equals blah, 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 x. So that means that when we draw it, and that's what it looks like when we draw it, it's not the sort of graph that you're used to looking at. On the x-axis is actually velocity. On the y-axis is actually displacement. So if I do a little g-solve here, and let's not do a g-solve. Let's just do a trace so we can sort of check out what's happening. Okay, so if we do a trace here, we can see that when x equals 0, and x is not x is v. That says when velocity is 0, the height of our object is 2.4004. I find it really hard to wrap my head around this graph because I'm not used to looking at those kinds of graphs. But if I just trace back a little bit, right, this says the displacement is 2.39 when the velocity is negative 0.22, right? That velocity, that negative, this side of the graph is when the thing's coming down with a negative velocity. So when the thing is going up, that's actually this part of the graph. Okay, when it has a height, let's go to the height of the child, which was 1.2 meters tall. So remember, the x values are our velocity, the y values are the height. So confusing, of the child. So 1.4. Okay, so when we were at a height of 1.39, the velocity was 4.555. If I do like an actual calc and find x equals 5, the velocity 5, which was our initial velocity, you can see we have a height of 1.19999. That's because of our rounding issues. So this graph you might find useful. You may also find it just hopelessly confusing. Either way, it's there, and that is a cool little acceleration question. Celebrate. All right, that's all we got. This was Guessing the Specialist Exam Part 4. Thanks always to my past students, fantastic people. Tell your brother, tell your sister, tell your cousin to go and check out the website, get some cool tutoring, get the newsletter. It is awesome. Catch you in the next one.